All right, now we are official. Okay, so let me begin by sharing the screen that I was sharing, and that was the book. Okay, share. Mhm. Okay, so let's see. Hold on. For some reason, I cannot view. Okay, there it is. So everyone hopefully can view this. So let me go over this again. So last week, again, we talked about Gaussian elimination and Gauss-Jordan elimination. I'll explain the difference between them in a moment. So first of all, we defined again a matrix to be a rectangular array of numbers that's made up of rows and columns. Now remember, the rows are labeled from top to bottom. So row 1, row 2, and so forth. So this matrix has m rows. And the columns, we go from left to right. So we have column 1, and then we have column 2, and so on, all the way to the nth column. So this matrix, therefore, is going to be a matrix whose size or dimension is m by n. It's rows followed by columns. Now remember, it's not commutative. So if I go n by m, that's a whole different looking matrix. So it's important that we keep the order of these straight. Every element of the matrix here for us is going to be a real number. And the A subscript 1, 1, that means the element in the first row, first column. For the subscript, so for instance, A sub 2, 3, that means this element is in the second row, third column of this matrix. So as you can see, row 2, and here I have column 3, and that's the entry in that position. Think of the subscript as the address for that element in the matrix. And what else? And then we looked at some example of matrices. And now the next thing we talked about, this is important. We talked about the elementary row operations on a matrix. And these same operations we looked at in section 1, where we talked about equivalent systems. Remember, systems of equations? So the first row operation allows us to exchange, swap, or interchange two rows. That would be like changing the entries in the matrix. Instead of writing equations 1, 2, 3, you can write them as equation 3, 2, 1, 2, 1, 3. It really doesn't matter. And then the second operation on matrices we said was that we can multiply a row by a non-zero constant. So if you choose to, you can multiply the row of a matrix by 7, as long as we multiply everything throughout that row by 7. And then number 3, often we use number 3 in order to replace a row of a matrix that we don't like the looks of it. We want to change it into another form. And this third operation reads add a multiple. This would be like a constant multiple of the row. So that's property number 2. You can add a constant multiple of the row to another row, and you can actually replace that row. And throughout this replacement process, the row that you multiply by the constant multiple itself will not change. It would often help us just to replace another row in the matrix. So for that reason, the constant multiple of the row that we multiply by, that row is called a quote unquote a helping row. It's going to help us get to another form of the equation. And Professor? Of course, we looked at, I think, some matrices where we did Gaussian elimination. The one thing that's important, by the way, what makes this the matrix, the Gaussian elimination allows us to write the matrix in its row echelon form. Remember, we talked about the row echelon form. And by that, we're talking about the stair-step formation that you see. So if you look at the system here on the left, we have x. Then the second equation, there is no x, begins with y. And the third one doesn't have x or y, and it has a z. Now, if you look at the system on the left, look at the matrix on the right. So this would be the matrix equivalent to the system. So this absence of x in the second row and absence of x and y in the third row cause zeros that you see here. The 0 in the second row, a 0, 0 in the third row for those missing variables. And this is again the idea of a stair step. So we call this matrix to be in its Gaussian form. It's just named in honor of Carl Gauss, Friedrich Gauss. So it's called the Gaussian form. Now, the reduced row echelon form, that's when we actually go back and create zeros anywhere you see a 1. You see that nice looking, beautiful diagonal of ones along the main diagonal of this matrix. You have 1, 1, 1. And then you have this nice triangular formation of zeros, right? The triangular formation here of zeros. Well, if we do the same thing, you make that 3 as 0, the 3 above that then as 0, and -2 as 0. So pretty much you're going to have a matrix whose diagonal is 1s, and the off diagonal is going to be 0. So when that happens, what you call it, when that happens, then we set the matrix to be in its reduced row echelon form. And that's what that one is. Now, if you look at this example, I like the highlighting of this one. And this is all from last week, folks, we're talking about. So you're looking at in part A, for example, this matrix is in row echelon form, isn't it? This part A. So is this matrix in its reduced row echelon form, though? What do you think, folks? In part A, is that in reduced or just row echelon? No, yeah, I'm reading the chat now. Okay, very good. No, it's not. And let me read also, Megan just send a chat. Okay, did I miss a lesson? I'm sorry. Oh, okay. Yes. Thank you, Megan. No, what I'm doing right now is I'm just quickly reviewing what we did last time in case a few people weren't there. So yeah, you're right. We did cover this last time. It's just I'm quickly go over it, and then we'll actually start tonight's lesson in about 10 minutes or so. So yeah, thank you for asking the question. Okay, so again, the answer, a couple of you put in the chat, that's correct. A is not in a reduced row echelon form. It is simply in row echelon. And by that we mean, see, the diagonal has to be 1, right? And below diagonal, you have 0, 0, 0. So this matrix is in echelon. To be in reduced row echelon, above the 1s must be 0 also, and they are not. See the 2, the -1? This 0 is okay, but these 2 are not. Now, what about a matrix D? What do you think, folks, in matrix D? Is matrix D in its row echelon form? What do you think? Yes, yes, and yes. Thank you. Very good. It is indeed. Again, notice highlighted in pink, definitely got the zeros here. And you also have zeros above the main diagonal. Perfect. So hopefully everyone's okay now with the idea of reduced row echelon form. Now, the matrix that is in row echelon form, like A, like C, we say that matrix is in its Gaussian form, Okay. Now, and then the matrix that's in reduced row echelon form, like D, the one we just covered, that's said to be in its Gauss-Jordan form. So for reduced row echelon, that means one's on the main diagonal, zeros above and below it. That matrix is in Gauss-Jordan form. Just terminologies there. Okay, so everyone good with the distinction between what's Gaussian, what is Gauss-Jordan form? So Gaussian again is echelon form. Gauss-Jordan means reduced row echelon form. And real quick, let me read. I have a message here directed to me. I guess I have a quick change from with other work. Okay, I leave meeting and watch recording. Yeah, absolutely. Let me, in fact, a student has sent me a private in the chat, private message. I am recording these sessions, folks, for the very reason, because I know being in the evening, sometimes you have other obligations, other commitments. I appreciate you all coming in. I mean, that really makes me feel good that you all come in and show up. But if for any reason you cannot make it, that's okay. I totally understand it. There's nothing personal. I don't take it personal if you don't come. I love for you to come. But if you don't, it's okay, because I'm recording the sessions. So when I'm recording the session, that means you're welcome to watch the session later on. It's as if you were here. So yeah, that would be perfectly fine. If you have to leave in the middle or miss, or for whatever reason, for any reason, that would be perfectly fine with me. Thank you for asking.
Could you, hopefully it's not too redundant. It's because I was having a hard time with my mic. Anyways, can you re-explain the reduced because when you will, can you go up a little bit, please?
Sure. Sorry about that. Hold on.
Yeah.
Let me go back to my, I don't know what happened here. Share.
Oh no, just the paper and the book.
Oh, right.
Oh, okay, I hear you.
It's not showing on on mine. I'm trying to regain it. Let me stop share and share again, because again, for some reason, it wasn't acting up. Okay, now I can actually see it. Okay, sorry about that. Go ahead, Jesus.
Can you scroll up a little bit?
Sure.
Yeah, there we go. You were showing us the example of A, and I mean, people say that it's not an echelon form. And
A.
then you went to example D and you said that that was echelon form. What is it again that makes it, I mean, row echelon form?
Oh, okay.
What is it again that makes it, uh, just to clear it up, what was it again that makes it row echelon form versus not? Because I mean, from what I understand, it's like if you have ones lined up, you can switch them to zeros, if I understood correctly. But
Sure,
then
absolutely.
after that, I don't see why A doesn't qualify if you have
Yeah,
ones lined up.
absolutely. So let me switch. And again, are you still, can you view the book page still?
Yeah, I can view it.
Okay, perfect. Okay, so let me explain again. Matrix A, matrix C, matrix A, C, and matrix F. Okay, so we have A, C, even D, and F. All four of these are in echelon form. So what does that mean? That means whenever you have a leading one, the leading one is just that. You have one, the row starts with one. Keep that in mind. It's called the leading one. So look at C. You have the leading one. And then beneath, directly below that, you got 0, 0, 0. So that's good. Look at the second row. So here's 0, so don't worry about that one. But look at the 1. So this is the leading one in the second row. Directly below that, you have 0, 0. That's good. And then in the fourth column, you have the leading 1, 0 beneath it, directly below it. And of course, in the fourth row, you have just 1. There's nothing below it, so that's fine, as long as we have these leading ones. The key is this, to have zeros directly below the ones, and we do. So this matrix is in echelon form. It's in Gaussian form. Now you look at the D, same thing. You have 1, 0, 0, 0 beneath. You have 1, 0, 0. You have 1, 0. And of course, the fourth row, there is no 1. So it's all zeros, and that's fine. So D is also in its echelon form. Okay. Now look at E, for example. E is not in the echelon form. And why do you think it's not quite in the echelon form? It's almost there, but there's just a little thing wrong with it. What do you
Because
think?
on the second column, it's leading with a 2 instead of a 1.
Very good. Exactly. So if this was 1, then E would be in the echelon form also. So are we okay on the echelon form part?
Yeah.
All right. Now let's talk reduced row echelon. In order for the matrix to be in reduced row echelon, the Gauss-Jordan form, not only beneath or below the ones there are zeros, above them, there should be zeros also. You see that, for example, in C, that's not the case. Where you see a 1, there is no 0 above it. You see a 1, there's no 0 above it. So C is not, it is in echelon, but it's not in reduced echelon form. Now look at D by contrast. In D, you have the main diagonal ones. It is in echelon. And look at the 0 above 1, 0, 0. That's good. This one, the middle column, the second column, directly above it, 0. So that is also in reduced echelon form. The last column, by the way, folks, don't worry about the last one, because this is a case of like a system of 3 equations and 3 unknowns. Remember, the last column is because these are augmented matrices. That means in a system, you have x1, x2, x3, each of those equal to a constant, right? So what it equals to, the constant, that's what these last numbers are in these columns. So we don't care about those constants in the last column. Those don't have to be ones. Those turn out to be a lot of times if the matrix is in its, for example, D, if it's in Gauss-Jordan form, the last column actually gives you the solution to these variables. So in D, the solution to variable, let's say Z, if it's X, Y, Z, the system, the solution to Z is 3. So that's the advantage, by the way. That's why we like matrices to be in their Gauss-Jordan. That means reduced row echelon form. So is everyone okay on this?
But just to double verify, on the third column, at the very top, we have a 0. I forgot how to call that. Maybe the first row.
This one?
What about if that was a number? Would it matter?
Yeah, if that was a number, whatever, then it's no longer reduced. Yes,
Okay.
sir.
It has to be exactly 0. That everything.
You got it.
All right,
So
makes sense.
you're welcome. Yeah, remember, you got to have a column, a diagonal of ones, and then off diagonal means to above it and below it. You have to have this triangular formation of zeros, which you do, and up here again, you do. That this is the triangular formation. I'm thinking 0, 0 below 0, 0. So that's what you got to do. Look at, for example, the matrix. How about matrix E? Oh, okay. Well, E we said is not in echelon form, right? If it's not in echelon form, then it cannot be in reduced, right? Because the process is you get it in echelon, the next step becomes reduced row echelon. So if E is not even echelon, then there's no way it's a reduced row echelon. So right there, that reduced part is out of the question. Now, what about F, by the way? Matrix F. First, is it in the echelon form?
Yeah, it is.
It is. Very good. Is it in the reduced echelon form?
It is.
Very good. You see that zero? Anywhere you have a one. If there is an entry, that means a number above it, it has to be zero. Now look at the second column. Here's a one, but there's nothing above it, so that's fine. This one, second row, third column, there is a one. There is an entry directly above it. It's zero, so that one it is in the reduced echelon form. So again, everyone okay on this, the reduced echelon form business? Now, don't worry, we'll go to applications in a moment. Now, one thing I want to do, and I mentioned that, is after, in fact, this would be a good place. You don't have to do this by hand. As you can see, the process is a tedious process. As long as you do it with like maybe two equation, two unknowns, three equation, three unknowns max, just maybe do it a couple of times, just so you see how the process works. But then we really are going to use software. And in fact, I'll show you right after this. I'll show you how to do this using a computer. We're going to go and I'll show you. So don't worry about this, Gauss Jordan. The software we use the portal we use is going to do it for us. So you don't have to worry about going through this painful process of doing all of these operations, elementary row operations, to get it into Gauss Jordan or reduced row echelon form. We'll let the software do it for us.
So just a question,
Yes.
doing the matrices, the way that, how you're having all that, it helps us solve multiple equations and at the same time, like how we were doing at the very beginning of class.
Let me make sure I understand correctly because my microphone was acting. Sorry about that. So, you talking about last week or tonight?
Yeah, last week. Like for example, you see in example number six, it gives us a problem of different equations, and each x sub is different. I mean, we can just say substitute x sub 2 for y, just for people to visualize it better. And then for x sub 3 is substituted for z
Oh,
if we
I
wanted
see.
to.
Yeah.
But anyways, long story short, would we be, are we solving that problem in the matrices?
Yes, sir. Yeah.
So
What
it's
we're
kind of like
doing.
a, oh, okay. It's a faster way of solving those equations instead of like, I mean, I felt like it takes longer the other way that we did it last week.
Right. Right. Now, thank you. Thank you for asking the question. So first, the answer, yes, we want to solve the system. So we want to know what x1, x2, x3 are. Now, you do x, y, z, that's fine. But keep in mind, we're going to stay with x1, x2, x3 for a reason. Suppose, and we will see tonight possibly, suppose I have a system that has 7 unknowns. It could happen, right? 7 unknowns. So if I'm using X, Y, Z, what am I going to use for the other 4?
The alphabet? I'm kidding. I'm kidding.
No, you're fine. Yeah, exactly. Maybe I should go then A, B, C, D, E, F, G, correct? So textbooks usually
Right.
don't do that. They don't typically for XYZ works fine, no problem. 3x3s and stuff, that's good. But usually beyond 3 equations, it's better to use aesthetically, looks better too. You don't have to deal with the alphabets. So this is very standard. All the linear algebra textbooks do that. For larger systems, we use subscripted variables. So x sub 1, sub 2, sub 3, sub 4, sub 5, sub 6, like that. It just aesthetically looks better. And that's, again, the norm, the common convention that textbooks have adapted to. So hopefully that answers that part of it.
Yeah, and then just to double verify everything that we're learning. Um, oh yeah, uh, oh yeah, there we go, I remember. So solving the system, solving each variable, how we did it last week.
Mhm.
You gave us 3 rules, which is how we started. you gave us like honestly I forgot them, but you
That's
showed us three rules. Those three rules apply to the matrices too, the
yes, sir.
bottom way of applying it.
Yes, and
Okay.
actually for larger systems, it's really a total royal pain in the neck to do that. That's what I'm saying. Don't worry about it. I'll show you how to do this using the software, and you're going to say, wow, this is so cool. I love this. So just bear with me for a few more minutes here, and I
Thank you. Thank you.
promise you're going to see. Don't worry, you don't have to do this nightmare by hand because it's very tedious. That's what I was saying. If you do it like in section 1.1, 1.2, two equation, two unknowns, just so you see the process like we did last week, like you said, it is a tedious process. So we really don't want to get bogged down with that because we want to do so much other stuff later on. I don't want to spend 30 minutes just trying to get this matrix from one state to another state to another state just to get it. And look at this. Look at the way this matrix looks. Is this matrix in Gauss-Jordan form? The last part. Let's see, I got 1, 0, 0, 1, 0, 5 right there. This is not in Gaussian. It's not an echelon form, is it?
No.
See, there's still more work to be done on this one. So yeah, this is a very long, tedious process, but I'll show you in just a few minutes. We're going to use a portal. We go online and I'll show you, and feel free on your own computers to do this alongside with me, and we'll see how this turns out.
One more thing. So, like
Yes.
the ones that are not in echelon form, we could make them in echelon form. Just because I'm still connecting the previous to the new way that we're learning.
Sure. Yeah. For this one, for example, what you need to do next is to, let's see, we need to make this, because it's not in, we need to get a 0 here, don't we? Instead of 5. So if I'm
Correct.
doing this for, let's say from last week, what am I going to do? I'm going to multiply the second row by -5 added to the fourth row, right? Because -5 times 1 is -5.
Correct.
Plus 5 is 0, and there you go. And then however these change, these change don't matter. Let's see, -5 times -1 is 5. 5 minus 7 is -2, right? So far, looks like I have 0, -2. If I do -5 times 2 in the second row, I get -10. -10 minus 11 is -21. So looks like if I multiply the second row by -5 added to the third and throw away the third row with a new one, it's going to be 0, 0, -2, -21. True? And even that,
Correct. And
even
then we can cancel the last row with the first row, right? Because you said -2, and we have +2.
Oh, if you do it with the first row, then see this -1 you see in the second column, first row,
Ah, okay, okay. I forgot about that one.
that's going to give us
It
trouble,
takes us back to the other way. Never
right?
mind.
So once this one is 0, remember, so next to that is going to be -2, next to that -21. Then this row just on its own, if this is -2, I'm going to multiply this row by reciprocal, -1/2. Just the fourth row, multiply by -1/2 after you replaced it. -1/2 times -2 is 1. Negative
It's one.
half times -21. So that's going to be 21
11.
halves. And you see how that works? And then this is a 1, we said, right? But so we go 1, 1, and then we're going to switch the third and the fourth row, aren't we? Because there is a 1 here now. We're going to make sure that lies up there. So I have that diagonal of 1s, right? So I need to
Correct.
switch row 3, 4. So again, there is a lot of work to be done, huh? The reason he stopped here, in this matrix is actually, look at the third row. What does this third row read? You have 0, 0, 0, -2. That means 0x plus 0y. If you go x, y, z, 0x plus 0y plus 0z equals -2. Well, 0 times anything is 0, right?
Yeah.
So this third row, he has it down here. That third row is saying, sorry, it says 0, this 0 equals -2. And that is not true. This is a false statement. That's why he stopped here. He said, oops, I see trouble in the third row. This system is inconsistent because 0 does not equal to -2. So he just stops. He said, there's no solution. The system is inconsistent.
Makes sense.
Yeah. Okay. So again, is everyone okay on this process? So we'll do again in just a moment. In fact, when we do the application, or let's actually do this. Just to show you how to use this software. This example 7, I'm going to write this matrix, and I'll show you in a moment on the paper I'm writing. I'm writing example 7, only the coefficients. So my first column is going to be 1, -1, 2, correct? The second column is going to be what?
Negative. Oh yeah. I mean, -2, 3, and 5. I mean,
Thank
negative.
you. Perfect. Thank you. Exactly. The third one would be 3, 0, 5. And the last one, 9, -4, 17. And you see how the last numbers here, the last numbers, the 9, -4, 17, I told you don't worry about those. We don't look at 1, 0, 1 with these because these numbers are to the right of equal sign. So we're looking at the matrix of coefficients. That's why the row echelon, reduced row echelon applies to these. Okay, it
Would
applies.
you be able to show us by hand how to do one? The only reason why is because I mean, I also want to learn how to do it by hand. I mean, I prefer the software, how you're gonna show us on the software, but would you also show us the
Sure,
option
sure. For this one, let me see. This
just
one.
for learning purposes?
Yeah, absolutely. Let me do that. So I'll show you what I'm writing here in just a moment. I put example 7. This is section 1.2, and let me do this. I'm gonna share my screen. Let me change my, I'm gonna stop this share and share a new one. Okay, so hopefully now, oops, I got so much technology around me. Okay, and hold on. Uh, wait, just 1 second here, folks. Sorry. Let me, okay.
Because I know, like, I mean, that would be pretty useful for like calculus 3 or like or
Sure.
like physics.
Oh, okay. Sure, no problem. Now I know what I can share. So I need to turn not yours, but my video off in Zoom because it cannot share my video as well as the video for the thing I'm using, OKO Cam. So I'm gonna turn off my video. Okay, so you should be able to see me now, and hopefully share. Okay. Can you see my notepad here?
Yeah, we can.
Oh, okay, perfect. So I just copied those coefficients, okay, from the book. Now, this was again example 7, right, in that section. So let's begin by, we got the leading one, right? First row, first column, we have the one there. Now, let's see, we need to turn this into row echelon form. So here is a 1. I need this -1 below it to be a 0. This one, we need it to be a 0. So is it okay if I simply add row 1 and row 2 together, these two rows? So let's do that. So we've got
Yeah, they'll
1.
cancel.
Okay. 3, 9. I'm just adding and replacing. That's rule number 3 of elementary row operation. So 1 minus 1. 1 minus 1. These I'm adding in columns. So that's 0. 3 negative 2, that's 1. 3 0, that's 3. 9 4, that's 5. Right, you see I got a 0 there. Now I need to get a 0 below that one. So how are we going to do that? Right now there is a 2 in that spot. So let's multiply the first row by -2. This first row by -2 added to the third row. So it goes -2 times 1, and then I'm adding it to the third row, replacing it. That's rule number 3 of elementary row operation we are doing. -2 by -2 is 4. 4 minus 5, that's -1. -2 times 3 is -6, plus 5, that's -1. -2 by 9, -18, and 17, that's -1. See how that works so far? So,
Yeah.
And then we got this nice formation 1 0 0. So that's good. And then we have the leading one in the second row, don't we? That's called a leading one, right? In the second row. Now I need to make this entry directly below 1 in that second row, second column. We need to make that a 0. How are we going to do that?
We can add it to the second, what is that, second row? Yeah.
You got it. You got it. 2, 3, 9, and second row is not going to change because it's good where it's at. This the second row, this row is called at this moment in the process, is called a helping row. You see that? It's simply helping us to get the third row into a form that we want. So we said let's add second and third, replace third row with that. So 0 and 0 makes 0. 1 -1 is 0. 3 minus 1 is 2. 5 -1 is 4. So far, so good. Okay, so we got 1 0 0
Yeah.
1 0. What else I need to do next?
Change the third column on the third row to 1.
You got it.
Yeah, if I said
Very
it.
good. And how do you think, or how do you propose we should do that?
Just turn it to a negative. Give me a minute.
No problem. No rush. It's a 2. We want to make it
Negative, will be, well, the thing is that it's going to be a -1, isn't it? If we multiply it by -2, because it will get -4, but plus 3, it's -1.
No. To create zeros, by the way, like we did here, 0 0 0, like that. To create 0, we usually need a helping row. Agreed? Now, to
Yes.
create a 1, we don't need a helping row. Remember, the second rule of elementary row operation says you can multiply any row by a constant. So 2 times what number becomes 1?
1/2.
Excellent. There you go. So let's multiply just the third row. So I'm going to leave the first row alone. We're going to leave the second row alone. Now, third row, 1/2 times 0. And 1/2 times the second 0. 1/2 times 2 is 1, and 1/2 times 4 would be 2, wouldn't it? Aha.
Yeah.
So question, is this matrix at this point in its echelon form?
Yeah, it is.
Very good. Echelon. Now, let's go a step further and make it reduce. And this is Gaussian. So right now it's in its Gaussian form. So let's do it using Gauss-Jordan now. We're going to write it in its reduced echelon. So in reduced echelon now, we look above the ones. See the 3 here? That's trouble. That 3 must be a 0. How do you think we should turn this into a 0? Remember, to make things into a 0, we need help from another row. So how do you think we should make that a 0 above the ones?
Multiply the second row by -1.
Now, if I remember, we want 0 here, right? If I multiply by -1, I get 0, -1, -3, -5. I still don't have the 0.
Oh, okay. We don't cancel it with the above with the first row.
Oh, okay. So, all right, I got it now. So you want to multiply this row, and in fact, let me do what you propose. Just we'll see what happens here.
I'm still
So,
learning, so I don't know if that's the right
no,
the right thing.
that's fine. Thank you for asking. Don't worry about it. So I just want to show, let's see if that works. If not, then we rethink it. So let's do by -1 as you proposed. So I'm doing -1 times this row. So I'm doing it on the side. So that would be a 0, -1, -3, -5, right? Now you mentioned add it to the first row. No problem. And there you go. That is the first row. Now let's add in columns here. So we're going to get 1, -3, 0. That's good. We got the 0 there, and then 4. Now keep in mind, when I write the matrix, first row, this will be a new second row, right? Because we added this -1 times second plus third to replace second. So look at my new improved second row. And what do you think? Is the C an issue with that matrix?
Yeah, we messed up the other form that we had. So I guess
Very.
it's kind of like playing like what is a game called? Rubric. So
Oh, yeah, I know.
so it's like you touch one, and if
Yeah,
you might mess it
exactly.
up in the other side.
And the rest fall
Okay.
apart. You got it. So you
Yeah.
see how this isn't going to help us doing that? No. So here's how we actually should do it. Then you say, well, then what's the correct way? What's the best way? Now, we want to make this a 0. In order to make this 0, use the row directly below it. And the reason is, see the entries in the third row, 0, 0. When I multiply third row by a number, these zeros won't change and it won't mess up the second row. Those entries, 0, 1s. We don't want to mess these.
Makes sense.
Because once you get it in the echelon form, it's like holding on to dear life. You want to hold on to 1, 1, 1, and then the lower triangular of 0. So let's do that. Is it okay then? We're going to multiply -3 now times third row added with the second row and replace the second row. So here's the first row. First row is just standing on the sideline and watching the process. I am not changing the third row. The third row right now, it's my helping row, acting as a helping row. So -3 times 0 is 0 plus 0 above. 0. -3 times 0, 0 plus 1 above. You see how we are not losing the 0, 1s in that second row? Look at this one. -3 times 1, -3 and 3. Aha, 0. -3 times 2, -6 plus 5. -1. You see what happens? So we got 1, 1, 1. We got our triangular 0. This is the triangular 0 I'm thinking of. And then we got 0 above the 1. Perfect. Next, we need to get this 3 to become a 0. And we're going to do exactly the same thing we just did. I'm going to multiply third row times -3. This time added to row 1. So we are replacing row 1. Row 2 pretty much is done. Row 2 will never be changed at this moment from here on out. Row 3 looks pretty. Row 3 will not be altered. We are working on row 1, trying to get rid of the -2 and 3. So -3 times 0. Remember, we're working with row 1 now. -3 times 0 plus 1. 1. -3 times 0, that's 0 plus -2. -2. -3 times 1 is -3 plus 3 in the first row. That's a 0. Aha. And then -3 times 2, -6 plus 9, that would be 3. Was that an okay step? Did it help us? It looks good, doesn't it?
To get closer, yeah.
See how we're getting one brick at a time. We're going step at a time through this maze. And believe it or not, folks, this is the most efficient method of solving systems. And the reason is because I know by hand it's a pain, it's a tedious process. But this whole process is programmed very easily in computer. The computer programmers have done this to where this is algorithmic. And here's what I mean, folks. The software we're going to use is going to do this. It's going to create this leading one. If it's not a 1, right in here, first row, first column, it creates the 1. Then here's how the algorithm works in the computer. It's going to go 1, make this a 0, make this a 0. It's going to go across, create a 1 here. Make this a 0. It's going to cut across, make a 1 here. Then it's going to go up, create a 0, go up, create a 0. Go to the left, create a 0. You see how algorithmic that was? In other words, here's how the process is. Here's 1. So the next step, this would be made a 0. Next step, this will be a 0. Then it will go across. It will create a 1 here. Then it will go below, makes a 0 here. That's the next position. And then it will go over, creates a 1 here. Then it goes above, creates a 0 here, 0 here, goes over, makes a 0. And this is what we mean by it being algorithmic. So if you do it by hand, it's like, my God, this is a nightmare, right? Who wants to do this? So let's do one more step. But this is great. I'm glad you recommended this. So we appreciate in the moment, we're really going to appreciate this software because it's going to make our lives so much easier. So now let's finish this. We got one more step and we're done, folks. We got -2 here. So what do you think we ought to do? We need a 0 there.
Can it be a 1 or not really? It has to be a 0.
It has to be a 0. Remember, above the 1s have to be 0. Above and below, actually, now. In reduced echelon, above, just like here, above or below. They all have to be 0.
Do we use the second row as a helping hand?
Very good. And what do you want me to do?
Multiply it by 2.
You got it. Now, again, we're working on row 1, so I'm going to repeat row 2. Remember, I promised row 2 and 3 will not get changed. And let's do that. 2 times 0 plus 1. You see, that's why we use this row. 2 times 0 is 0 plus 1. We're not going to lose that important leading 1. It's still 1. 2 times 1, 2 minus 2. Aha, beautiful. Sure. 2 times 0, 0 and 0, 0. 2 times -1 plus 3. That's 1. So you see, this is gorgeous. We got this triangular formation of 0 above. You got the lower triangular formation, ones along the main diagonal. And at this point, because the matrix is in its reduced row echelon, if you think of X, Y, Z, what does the third row tell us about the system?
The Z equals 2.
You got it. You see how if we are actually looking at the solution to the system.
Yeah.
What does the second row tell us?
Y equals -1.
Oh, perfect. And finally, X is 1. So you see the advantage of reduced row echelon? It actually solves the system. Once we get it to that point, the system is solved.
That's amazing.
You're right. It is amazing how that works. So again, keep in mind, from here on out, we're going to use, and in fact, we saw the answer to this one. You have it in your notes if you wrote it. I have it in mind, certainly. So let's actually do this with the software, shall we? Let's see how this is going to work. So I'm going to stop my share and change my share to the software now. Okay, so there you go. And share. Here we go. Okay, so hopefully everyone can see this site called Symbolab. Everyone can see this one, okay? All right. Now, and this side, by the way, it helps you with your pre-algebra, algebra, pre-calculus, calculus, trigonometry, statistics, physics, chemistry, finance, economics. See, it's really an amazing site, folks. So you can use it actually if you're going to take calculus, you're in calculus, maybe Calc 3 right now, whatever. See, it does all of that good stuff. ODE, ordinary differential equations, it can solve that. So anyway, we are on linear algebra. So I clicked on linear algebra and this is what I got. Now, let's actually do Gauss-Jordan. So I'm going to click on Gauss-Jordan. Now, if I go too fast, please tell me so I'll slow down.
Gauss-Jordan is the reduced echelon form, right?
Yes, sir. That's the form. From here until the end of the course, this is what we want. We want Gauss-Jordan. Okay. So Gauss-Jordan. Now the matrix we are about to do, what's the size of the matrix we just did in example 7? How many rows? Good. It's a 3 by 4 size of the matrix, isn't it?
Okay. Yeah, because of the answers.
Exactly, because you got 3 rows, 4 columns. So here's a 3 by 4 already in there. So I'm going to click on 3 by 4. Now, or that's the quick way to do it. If you want, by the way, you say, well, I have a 7 by 8 and I don't see it here. Then you go here. You see that? Select matrix size. So I'm going to select it this way just to show you how it works. Now, the way this works, you don't have to click the mouse. Just hover the mouse. I'm hovering the mouse over it. See how this is going crazy? So I want to have 3 rows, 4 columns. So I'm not clicking, folks. I'm just hovering the mouse over. Here's 3. Left, it was 3. Then you go to the right, 3. Isn't this a 3 by 4? That's what we want.
Yeah.
And now just left click once. Boom. So this will do any size that you want. These are just preset, just to make it go quickly. So now I'm going to put in only the coefficients, and please check, make sure I'm putting the numbers right. So I'm going to put 1, right arrow, -2. Let me use tab. Okay, good. So the right arrow and tab both work. And then it's 3. And again, please make sure I'm inputting these correctly. The first row looks good. This is example 7, the one we just did. And then we're going to go -1, arrow to the right, 3, 0, -4. And the last one is 2, -5, 5, and 17. Give you a moment to verify that for me, please. Does everything look good on that one? This looks okay.
It looks good.
All right, thank you. So now check this out, folks. Like magic, you see the go button here? Boom, and check below. Amazing. Here's Gauss. It says the part says, so you're doing Gauss-Jordan of this, and look at the solution, folks. Isn't that what we did after 1, 2, 3, 4, 5, 6 matrix later?
So it was like 15 minutes.
Exactly. So that's why I said we don't really want to do this by hand, do we? No one does this by hand, folks, other than just for illustration. So we know, yeah, okay, I've seen the process. I know I appreciate how it works, blah, 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 but then we really don't want to do it by hand. And you're welcome to use this, by the way, on homework and on the exam even. And I encourage you to use it on the exam. Imagine if you do Gauss.
Are you referring about the website or about the Gauss-Jordan form?
Oh, okay. So let's say this was a test question. The question says solve the system, right? Like example 7. All you got to do is come here, put the numbers, hit Gauss-Jordan, get this, what you see the solution here, right? You see that?
Yeah.
And then from this, just give me the solution and you're done.
Wow. It's amazing.
Yeah. And again, because there's no point in making you do this. And you'll see, we'll do an example in just a moment, and you will see the system we're going to work with is going to have like 6 variables and 6 equations. So we don't want to do that. Imagine doing that by hand. My gosh, the rest of the session, we have to do that. So it's really not efficient, and it's not supposed to be that way. So is everyone okay on how to use this symbol lab? For now, the Gauss-Jordan part, we're good?
Yeah.
Fantastic. Good. So that was the big part of what we did last time. Now, let's actually, don't worry, in section 1.3 that we are about to do, and let me change my share here. So I'm going to stop the share and share a different screen with you. I'm going to share the book again. Okay. Now we can actually go to section 1.3. Oh, the homogeneous system, remember, that's a system that has all zeros on the right side. Every equation equals 0 is called a homogeneous system. Every homogeneous system has a trivial solution. If the sum of these variables is 0 in every equation, well, one solution is make everything 0. x1, x2, x3, xn. Every one of them is 0 because 0 equals 0. That is called the obvious solution. We don't want the obvious. So if the system has non-trivial, we would like that. Okay. Now, let's go to section 1.3, and we'll look at the applications. Now, there are several applications. The ones that we are interested in, pretty much the instructors pick and choose the applications that they like or whatever. So for the work we do, let's take a look at the application to network analysis. Okay. Now, and we'll do an example here in a moment together. So, so this is actually what you're looking at. You have a branch. This is a junction, the one that's in color, the circle, that's a junction. It would be like, for example, in traffic, if we apply this to traffic flow, this would be like an intersection. An intersection like, I don't know, San Marcos Boulevard and Main Street. So this is a junction. So for instance, I can think of 25 as 25 vehicles coming into that intersection. And suppose that intersection, there are two routes, two streets, two ways to get out of the intersection. So the flow in of these 25 cars, vehicles, whatever, the flow in should equal to the flow out, doesn't it? Otherwise, there will be a congestion at that intersection, wouldn't it? We want things to
Yeah.
flow. Okay. So therefore, it makes sense for this equation to have, right? Shouldn't the total leaving the junction equal to the total entering the junction at that point?
Yeah.
Okay. And there you go. That's why x1 plus x2 is 25.
I mean, although like the previous examples and those things, I mean, I thought we were thought that the inputs are whatever we put in for x sub 1 or x sub 2, and the output is 25. But I mean, if that's the case, then it's also the case that the input can be 25 and the output can be the x sub 1 and x sub 2. I guess
That's correct. That is
like
correct.
bilateral. I mean, that's
Yes.
why we learn in physics, you know,
Yeah,
because it's a
exactly.
two-way street.
Sure. You got it. You got it. So that's why this, or they could, for example, this one, they could have x1, x2 coming in, leaving as 25. You see that? So the flow from one branch, flow from another branch in here at that junction equal to the flow out. Again, that's if we don't want any congestion or backups in the network. We just want things to flow. And in a moment, we do an exercise together, but this example again. So look at here, we got 1, 2, 3, 4, 5 junctions. So we can actually create a system out of this. And this is what the system is going to look like. Again, we'll do our own in just a moment where we model it ourselves. But here's what I was talking about. Look at this one, folks. This is the augmented matrix. And of course, it's good. It's got a bunch of ones and zeros, right? But
It's horrible. Okay.
horrible. Check this out. And you can try if you want to. I would not do it, honestly, folks. But if you really are up to challenge, you have nothing better to do later on, you say, okay, I'm going to do a Gauss-Jordan on this one. But we're going to use Symbolab. And check this out. Is this matrix in its Gauss-Jordan form?
Not yet. I
See,
mean, it's in its echelon form, but not its reduced echelon form.
actually, it is in um, a reduced echelon form. And the reason is this. You see the one?
Yeah.
0 below. The 1, 0 below, 0 above. The ones are the key here. See the 1?
Okay.
0 below, 0 above. 1, 0 above, 0 below. This one is 0, not a 1. So this is in its reduced row echelon form. There's no way I can make this a 0, this one. I cannot make that one a 0 because to make this a 0, don't I need this row, the last row to do it?
Yeah.
This one? Well, it's a 0. No matter what I multiply by 1. 1 times 0 is 0. So there's no way I can make that a 0. So remember, for reduced row echelon, you have to have the leading row, and above and below that, it has to be a 0. Okay. And I'm sure that at this point they used the software. Nobody did this by hand. I guarantee you that. And there you go. At this point, we can actually now look at the solution. X sub 1, sub 2, sub 3, sub 4, sub 5. So the fourth row. The fourth row, remember this one is the coefficient on x1 to x sub 4, isn't it? So this fourth row, what does the fourth row tell us? What's the expression, the equation for the fourth row?
Saying that 1, 2, 3, 4.
Tells us we have a free variable.
It's x sub 5 is 1.
Good. This one says x sub 4, right? Minus x sub 5, right? X sub 4 minus x sub 5 equals 10. That's what this one says. And that's this equation right there, right in here. Would you agree? That's what that reads? Look at the first row, just the first row. What does the first row read? X sub 1, 2 is 0, 3, 0, 4, 0, minus x sub 5. Isn't that what this one is?
Yeah.
So x sub 1 minus x sub 5 equals negative 10. That's the first row. And then once you write these, and then we have to determine the solution. These would be reduced form. It cannot get any simpler than this, the matrix. The Gauss-Jordan is the ultimate simplification of the matrix. Now, from this ourselves, we can come up with a solution. Remember, the way I work this now, I look at the matrix, and you see this negative 1 in the last, in this column, in the fourth row. Would you agree there's nothing we're going to gain from the fifth row of this matrix? It's 0, 0, 0, 0, 0, 0. So just ignore the fifth row. Now look at the fourth row. The fourth row we said is x4 minus x5 is 10. So what we do is we're gonna let this variable x sub 5 to be our free variable. Remember we talked about free variables last week. That's when we let x sub 5 be t, the generic t here. Okay. And then if x sub 5 is t, then in the equation x sub 4 minus x sub 5, 10. Plug in the t for x sub 5. Again, we'll do one in a moment ourselves. I'll just try and explain this. You let x sub 5 be t, so x sub 4 is 10. Move it to the other side, plus t, isn't it? And there you go. That's how he gets x sub 4. So the last variable, remember, we're going to let the last one be our free variable. That's what that is. Is everyone okay with this?
Yeah.
All right. Now, the one more thing, and then we'll do an example. Then we'll take a short break here. I know you guys are getting tired. The other example here is very applicable to electric circuits. And eventually, I'm sure some of you will take a course in electric circuit or electronics, and you will see this as a very important law. It's called Kirchhoff's law. Kirchhoff, named after the Russian engineer. Kirchhoff's law, there are two laws for Kirchhoff. Okay, this one. Law 1 of Kirchhoff says all the currents flowing into a junction must flow out of it. It's kind of like the network, isn't it? Now, Kirchhoff law applies to electrical networks. It's meant for electrical networks, but you can apply it kind of to our traffic flow network. And this is definitely number 1. So, except here, the current, we're talking about current in a circuit. You talked about current, you talked about voltage, things like that, resistance. So we're talking about current. All currents flowing into a junction must flow out of it. Okay. And number 2, the sum of the product IR. The IR in electrical field means voltage. You may remember this from physics, folks. Remember V equal IR? Hopefully you do. If not, I'll write it down. V is voltage. That's the relationship between voltage, the current, and the R is the resistance. The voltage is current times resistance around the closed path. The sum of these voltages equal to the total voltage in the path. Okay. So there you have it. And here's an example of Kirchhoff's law. Okay. So here you have a path, and this looks like a circular arrow. This is the flow of current through this what you call it, electric network. So the top portion, the flow is to the left, then down to the right. So it goes junction 1, goes to 2, goes back up. See how the circuit is a closed circuit. So this is how the flow is. Now look at path 2. It goes in a clockwise direction. So for path 2, flow out of junction 1, comes through to 2, goes down to the left, through the battery, and then goes here, goes back to 1, and it cycles through, goes to 2, down, left, up, through, down. So that's how this circuit works. Okay. All right. Now, let's actually do an example ourselves. And we'll look at this one, guys. Wow. 1, 2, 3, 4, 5, 6, 7 equations. 7 equations, 2, 4, 6, 2, 4, 6, and 6 unknowns for this one. Imagine doing Gauss-Jordan. And look at what they've done here. Using Gauss-Jordan, a graphing utility or software program. And that's what they're doing. Again, nobody does this by hand. We really don't want to torture ourselves that bad. Not on a Wednesday evening anyway. All right. So let's actually take a look at, or what if we do this? Should we, let me stop recording. That's fine. I'm going to pause, not to stop. Sorry, let me pause it. Okay, so let's do this then. Let's actually go through and do an example. We'll do a couple of exercises in this section, and then I think that will help us quite a bit. The exercises are going to go quickly because we're going to use technology in order to go to the to turn the matrix into reduced row echelon form. So allow me to share my screen first of all. I'm going to share it. Come on. There you go. That's the page of the book. And in section, let's see. There you go. Let's take a look at exercise number 30 in this section. All right, so in exercise number 30, it says the figure, and hopefully you can see. If you cannot see my screen, please let me know. Otherwise, I assume you can see it. It reads, the figure shows the flow of traffic through a network of streets. So there you go. This could be some kind of a location downtown San Diego. It could be anywhere. Downtown Escondido, so any place where there is traffic flow. Now, in part A, solve the system for x sub I, where I is 1, 2, 3, 4, and 5. So you can see x sub 1, 2, 3, 4, 5. So it looks like we have 5 unknowns. So let's see how many equations we're going to come up with. Just looking at this graph, by the way, how many equations you think we're going to come up with, everyone?
5.
How many equations?
5.
5.
5.
Exactly. We would hope we have 5, right? Because there are 5 variables, right? So we are hoping to have 5. Now look at the number of junctions. Each junction is going to give us an equation, isn't it? Flow in is equal to flow out at every junction. So I'm going from top left, clockwise rotation. So let's say junction 1, 2, 3. Looks like we have 4 junctions, right? So from the looks of it, we're going to have 4 equations and 5 unknowns. So we're not going to get 5 because we don't have 5 junctions. Okay. Now, is that okay? Everyone sees why? Now, if you're okay with that. And then in part B, find the traffic flow when x sub 3 is 0 x sub 5 is 100. These are just plain what if game. What if no car is going from here to there? So this is less traveled. A road that's not used often. So x sub 3 is 0. And x sub 5 is 100. So 300 comes in, 100 leaves this way, and x sub 3, 0 goes that way. So that should be, that should help us find x sub 2, huh? Once we have,
I'm not quite sure how to help you with that.
and then once we have x sub 2, then we can solve this system. All right, so shall we get started and work this one together?
Yeah.
All right, fantastic. Now let me change my share. So this one, I'm going to graph this on my paper, and I'm going to switch to my, what is it called? It's called OQ Cam. Yeah, I'm going to switch to my OQ Cam. And let me stop this share and change my share to OQ Cam. And for this one to work, I have to turn my video off. Sorry about that, folks. Is everyone okay? Can you see the note I have in front of me?
We can see it.
Perfect. Thank you, everyone. All right, well, let's do this. Now, I'm looking at the page of the book, okay, number 30, and I'm going to redraw it over here. So this is in section 1.3, and exercise is number 30. Now, here's the way I look at it. This is junction, call it junction 1. I'm going in a clockwise direction, just conventional. You don't have to go clockwise, but if you do, you get exactly what I got. So this is junction 2. I'm looking at, again, the page of the book, everyone. So it looks like 600 is leaving. X sub 1 is what's flowing into 2. Junction 1, from the left, it looks like 400 vehicles are flown into that junction. And there are 2 ways, one x sub 2 from the south coming into junction 1, and then leaving junction 1 is x sub 1. At junction, this one, again, 1, 2, and this goes this way. This flow is x sub 3, that branch. From 2 flows down to junction, so this is 3, that would be 4. From 4 to 3, this would be x sub 5. Leaving junction 3 to the right, going, let's say, east is 100. From 2 to 3, junction 2 to junction 3, x sub 4. And this is going to be 300 coming into junction 4 from the west. So again, I just copied what's in the book. That's all I did. Now, we want to look at the flow of traffic through this. So in part A, the question reads, solve x sub I for I 1, 2, 3, 4, 5. So that means x sub 1, 2, there you go. We want to solve for that. Now, remember, in order to do this, we need to come up with a system of equations. So feel free to chime in, everyone. At junction 1, we can come up with an equation for junction 1. What do you think? So here's junction, short, J-N-C-T, junction, junction 1. What do you think the equation would be for junction 1? Anyone?
x2 plus 400 equals x1.
Excellent. Thank you very much, Ariana. Everyone okay with that one? Remember, at every junction, the flow in should equal to flow out. So in junction 1, you got 400 going in from the left, from the west, x sub 2, however many coming from the south, the 2 enter and x1 leaves. So let's do that. I'm going to write x sub 1 is equal to x sub 2 plus 400. Thank you. How about junction 2? This one. At junction 2, hope we can see better. Again, what flows into 2 is from the left, right, and the diagonal. So 2 routes go in, x sub 1 and
Is
x
it x sub 1 plus x sub 3 equals 600? Or
E-
the rewind? Or
good.
the reverse version?
X sub 1, x sub 3, 600. Is that all?
Oh, I'm sorry. I didn't. Oh, the equal plus x sub 4.
Very good. Yeah, no need to be sorry. That's fine. Perfect. Right? Because you have, again, from 2 sources come in and 2 lead out of it. Thank you. Very good. Thank you, Jesus. Let's go to junction 3. What about at junction 3?
X4 plus X5 equals 100.
Thank you, Ariana. Thank you. Exactly. So x sub 4 plus x sub 5 equals 100. Thank you. And finally, junction 4. So now we're looking at this guy. At junction 4,
You do
X,
300? Oh, somebody else was going to say?
sorry,
You can
and
say.
that's fine.
X2 plus X3 plus X5 equals 300.
Thank you. Fantastic. Thank you, Mr. Kai. X2, X3, X5, those are leaving, right? The leaving junction for leaving. So they add them. The total is what flows into that from this source, wherever that's from. 300. Perfect. Is everyone okay on how we came up with the system? All right. If you're good. Now we need to rewrite this as a system. So let's begin with our junction 1. How can I write the system in standard form? Remember, in standard form, you got your variables, and then you have the constant here, right? So that's what the standard form is. So let's say for this first junction 1, what would be the standard form of that equation?
X1 minus X2 equals 400.
Great. Thank you, sir. Appreciate that. Now, because we have x1, 2, 3, 4, 5, so I'm going to go x1, 2, pretend, x3, pretend, x4, pretend, and x5 equal 400. See, I'm just spacing it out as if I had x3, x4, x5. Okay. And how about junction 2? This one, we got x1 and 3, right? They're on the right, not meaning literally right, but they're in the correct position. They're on the left, to the left of equal sign. When you think about x sub 4,
We would have that as minus X sub 4 on the left.
you got it. So we're going to line up x sub 1. We're going to push x sub 3 to the side, as if again x sub 2 is there. And as you mentioned, we're going to bring x sub 4 on the left. It's now negative. Positive on the right means it becomes negative when you move it to the left. And we have the constant 600. See how we are forming the matrix, and we are about to ready. When we're done, we will feed this into Symbolab, and we have the answers. Isn't that cool? Let's go junction 3. What do you think about junction 3? That would be this.
It's good, sis, right?
You got it. This one is good the way it looks. It's in the right form. It's got the variables on the left, the constant on the right. So it is in the right form. So let's just write that one. So it's going to be, we mentioned it's x sub 4 plus x sub 5 equals 100. Perfect. And last not the least, junction 4. What do you think?
Same thing.
Keep it the way it is?
Yeah,
Looks
it's the
good.
same thing.
You got it. X sub 2 plus X sub 3. And now it's X sub 5, isn't it? So I need to space it. And again, this is for aesthetics, everyone, what we're doing here. And that's 300. The space in it, you see the spaces here, 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 here. That's just to make sure everything looks in its appropriate position. So everyone okay with the system being that?
Yeah.
Perfect. Now let's create the matrix. Now for matrix, you're welcome to use like angle, straight brackets, or I'm going to use parentheses because Symbolab does that. And if it's okay, if you do it like this is fine. If you use straight brackets, that's fine. I'm going to use parentheses like Symbolab does. Okay, what would be the equation? We're trying to write the augmented matrix. What do you think the augmented matrix will look like for the first equation?
1 and -1 and 400.
Thank you. Perfect. 1, -1, 400. And again, if anyone has question, by all means, feel free to interrupt us and ask questions. Okay, and how about second equation?
So I'll let somebody speak.
Sure. The second equation, we're looking at again the augmented matrix for the system. What would be a row in the matrix equivalent to that second equation? This is 1. There is no X sub 2, right? So it will be 0. Oh, and by the way, so sorry, forgot to leave the zeros here. Because, okay, going back to the first one. 1, -1, 400. So that means the other 3 are zeros, aren't they? So that's 3, 4, 5. Those are the coefficient on X sub 3, 4, and 5. Okay, the second row is going to be 1, 0, 1, -1, 0, 600. Is that correct?
Yeah.
Perfect.
Yeah.
What about the third equation?
0, 0, 1, 1, 0, 100.
Thank you. Exactly. There are no x1, x2, x3, so those are zeros. And then you got x sub 4, x sub 5, 1, 1, and there is your number. Thank you, Ariana. Let's finish it off with the last equation. The last one will be 0, 1, 1, 0, 1, 300. Is that correct?
Yeah.
Perfect. Now, I know this is not in the Gauss-Jordan form, but we can actually come up with equations on this one. But let's go ahead because we will convert everything to Gauss-Jordan. Let's go to a Symbolab and turn this into a Gauss-Jordan form. So I'm going to have to stop this and change my share with you. Stop share. And let's share to Symbolab. All right. And so I'm in Gauss-Jordan. I'm going to delete that matrix. So our matrix is what's going to be the size of the matrix we're going to need here? How many rows?
It's a 4 by 6.
Very good. Thank you. 4 by 6. Now notice I don't see a 4 by 6 here. You see that? But that's no biggie. Again, you hold your mouse. Don't click it. Please just hover the mouse over. So I'm going to go 1, 2, 3, 4 rows and 6 columns. 2, 3, 4, 5, See, and then if you left click once, that's all I need to do. And up there, by the way, see how I've selected the shaded. Above it, it says select matrix size. Right now, it says it is a 4x6. So if I go here, that's 8x9, 7x2, 1x6. So we want a 4x6, and there you go. That's just easy read. Just left click once, and there you go. Let's plug in the numbers, ladies and gentlemen. I'm going to go 1. Now you can tab over or just do the right arrow. I'm using right arrow on my laptop. -1, and then we got 1, 2, 3 zeros and a 400. Right arrow, 1, 0, 1, -1, 0, and 600. 1, 2, 3 zeros, 2 ones, and 100. And finally, 0, 1, 1, 0, 1, 300. Give you a moment to just kind of make sure I got it right and it matches what you have. So everyone hopefully with us. And now I'm going to just hit go here, right there. Click on the red go, left click once. And there you go. Here's your Gauss-Jordan. Now, interesting, if you look at the Gauss-Jordan and, and look at what we have, what do you think? I mean, oh, sorry about that. I was looking at this one. That's not the, I was going to say, wow, it looks the same. But actually here, it echoes the problem. And here's the solution. There's the Gauss-Jordan. Isn't that cool? So I'm just going to go ahead and write this down on my paper. Then I'll show you my paper. So I'm going to go 1, 0, 0, 0, 0, 1, 0, 0. I'm going one column at a time. Third column, 1, 1, 0, 0. Fourth column, 0, 0, 1, 0. Fifth column, I've got 3 1s and a 0. And the numbers. Got 700, 300, and 100 and 0. Okay, so we're good on that, everyone? Now,
Yeah.
Perfect, thank you. Okay, well, clearly the last row is not going to tell me anything, right? There's just 0, 0, 0, 0. So we're just going to ignore that one. What does the third equation read? The third equation.
X4 plus X5 equals 100.
Thank you. I'm going to write that, X4. Oh, actually, now that I've written, let me go back to my OQ cam because now we're actually, hopefully, again, everybody's good. Please copy this one. I did it on my paper. I'll show you in a moment. So let me stop share and change it back to my note. All right, so this is where I'm at. All right. Looking at the third row. Remember, for the columns, if it helps you, you're welcome to do this. You don't have to. If it helps you, do it. X sub 3, X sub 4, X sub 5, right? So these are just the coefficients on X sub 1. The coefficients in that column, X sub 2, X sub 3, X sub 4, and X sub 5. All right. So the third equation, the ones with 0, we can just ignore them. That's 0x1, 0, 0. That's just 0. Now, 1 x sub 4, that's the coefficient on x sub 4. So it's going to be x sub 4. And then plus x sub 5 equals 100, right? Now, what are you going to let your free variable be? Let free variable be in that equation.
X5.
Thank you. Be x sub 5. Again, free variable means it's free to take on any values. So we're going to let free variable x sub 5. What does that mean? That means x sub 5 is t there. The parametric solutions. Remember, to begin with, we knew that we don't have enough equations to account for all variables, right? We have 1, 2, 3, 4 equation, 1, 2, 3, 4, 5 variables. So we're not going to be able to solve this and get a unique solution. So that means we're going to have a parametric form of the equation. Generally, the last variable, we're going to let that be our free variable. So hopefully everyone is okay with this choice. Now, if that's the case, let's go to the second row, second equation. This, what does this read?
X sub 2 plus x sub 3 plus x sub 5 equals 300.
Perfect. Thank you very much. Equal 300. Now, we already have a free variable, right? X sub 5 is t. We know that one. So I'm just going to hide it, cover that one. What do you think? We're going to let x sub 3 be?
S.
S. Excellent. This is our other free variable. Let free variable be x sub 3. That means x sub 3 is now S. Perfect. So now we can write x sub 2. Isolate x sub 2. That means that's 300 minus t. Remember, x sub 5 is t, minus t, and now minus s. Good. So we got x sub 5, we got x sub 3, we got x sub 2, and let's move on to the first one. What does the first one read? Oh, let me see, x sub 4. So sorry, I didn't write x sub 4. I said it and then I didn't finish it. I'm backtracking to this one, folks. This one. I talked about it, but I didn't finish. So would you agree that x sub 4 is 100 minus x sub 5? That's 100 minus t, isn't it? We're good? So we got x sub 5, x sub 4, x sub 3, x sub 2. The only thing that remains is x sub 1. Let's go to our first equation. What does it read?
So the fourth equation or which one?
The first equation. We're looking at first.
Isn't it x sub, is that 1?
Yes, that's x sub 1, the first variable. So it's 1x sub 1. So that just means x sub 1 plus
X sub 3
x sub 3
plus x sub 5.
plus x sub 5 equals 700. Let's solve for x sub 1 now in this one. Let's solve for x sub 1. X sub 1 would be 700 minus x sub 5, but isn't x sub 5 t? So that's going to be minus t. Minus x sub 3, because we move x sub 3 to the other side. Minus x sub 3, but then x sub 3 is s. And there we have this one, ladies and gentlemen. So we have solved the system parametrically. We have the solution for x sub 1, 2, 3, 4, and 5. In other words, the system has infinite number of solutions, doesn't it? So this is the answer to part A. Is everyone okay on part A now?
Yeah.
Thank you. All right. Now in part B, let's do part B. And for part B, let me do this. So we're doing part B now. In part B, I'm reading again from the book. In part B, it says, find the traffic flow when x sub 3 is 0, x sub 5 is 100. X sub 3 is 0, x sub 5 is 100. Now, if you note, x sub 5 is the t, isn't it? So that means when t is, in other words, 100, x sub 3, isn't x sub 3 s? So that means s is 0. True? So find the traffic flow. In other words, we need to find what x sub 1, what x sub 2, and what x sub 4 are going to be. What will x sub 1 be? X sub 1?
700 minus t minus s.
Exactly. And t is 100, and s is 0. So that would be 600. X sub 1, 600. What about x sub 2? Same thing, right? We're going to plug in for t, 100, s, 0. So x sub 2 is going to be 300 minus, I'm just going to rewrite it and plug in the numbers. 300 minus t and minus 0. So that's going to make it 200. X sub 2 is 200. 1, 2, well, x sub 3, we are given, right? That was given 0. I'm just writing the whole solution here. And x sub 4, we are about to do x sub 4. X sub 4 is right up here. It's 100 minus t. But then t, they gave us to be 100. So it's 100 minus 100. And that would be 0, wouldn't it? So x sub 4 is 0. And x sub 5 was given. That would be 100. 3 and 5, those were given in the statement of the problem. And there is the solution. Is everyone okay with that? All right. So if we're good, now let's go finish it off in part C. In part C, the question reads, find the traffic flow.
Could you move the paper up? It's because the part of the the Oki cam is blocking the writing.
Oh, I'm sorry. It's like this part. Is that okay?
We're good now. We're
Okay.
good now. We're good.
Okay. Yeah, thank you. Please, if something is visually distracting, please let me know. Okay, so there we have that one. Now in part C is kind of like part B. It says find the flow when x sub 3 and x sub 5 each have the same number of vehicles. 100 flows through x sub 3, x sub 5. Remember, here is our S and here is our T. So we're just going to play those into our variables. So x sub 1, again, x sub 1 is right here, 700 minus t minus s. So it's going to be 700 minus t minus s. That will be 500. So now x sub 1 is 500. Got x sub 1. Let's do x sub 2. X sub 2 is here. X sub 2 is 300 minus t minus s. So it's 300 minus t is 100. S is 100. That would make it 100. So x sub 2, 100. And now we are x sub 3. That was given. X sub 3 was given to be 100. X sub 5 was given to be 100. Those were given from the statement of the problem. And x sub 4 is going to be 100 minus t. That's 100 minus t is 100. And this time, x sub 4 is 0. And that would be the flow through that segment or that grid that we were looking at. Is everyone okay on this example, on this exercise?
Yeah.
We're good. Fantastic. All right, let's take a look at another one. Okay, so I'm gonna I'm gonna stop this share, go back to the page of the book. All right. So let's take a look at this one now. And we just finished number 30, right? That's the one we just did. It was number 30. Now, let's take a look at, how about number 32? Let's take a look at number 32. Wow, there you go. In number 32, this is now again network analysis. The question, determine the currents I1 through I6, right? Sorry, I1 through I6 for the electrical network shown in here. And there we go. We got this nice looking electrical network. Okay. Now, for this one, we do need to kind of draw the arrows ourselves. You remember in the example, he had those blue circular arrows that show the flow. So this is what I'm trying to do. I'm following the first arrow on top. You see that coming out of a 14-volt battery? The arrow goes to the left, doesn't it? So in this segment of the network, the flow is to the left, goes down this junction, and it goes to the right, doesn't it? Goes through this node, comes back up. So you have a complete circuit. True? That's what this one is. Is that one okay?
Yeah.
All right. Now, so this is the top one. The top one is going to go counterclockwise. And I'll draw this again on the paper. You'll see it. I just wanted to mention it so you see where I'm getting these clockwise, counterclockwise arrows in a moment. Now look at the middle part. The arrow on top, right in here. It goes to the right, goes through here, right? We're looking at the middle part. Then it's going to go down, come down, then turns left, and it goes back up, and it goes around, doesn't it? So it looks like in the middle segment, the flow is it clockwise or counterclockwise?
Counterclockwise.
Remember see how it's going? It's
Oh,
going.
that's clockwise. My bad.
Yeah, no problem. It's going to be clockwise, right? Because it's going again, circling in a clockwise direction like that. Good. Now let's look at the last part. Comes from the arrow from the bottom, comes, goes back up, and it goes through this resistance, gets to the node, comes back through. And so the flow of the last segment, the current is flowing in counterclockwise, isn't it? Okay, so let me now draw this on the paper. So while you're looking at that, I'm just drawing it. Just give me a few moments here. Okay, left down, there's the junction. And then to the right, I've got the 2 ohms of resistance. And it goes to that junction. Arrow right, above arrow left. I sub 1 on top, I sub 2 on the bottom. Okay.
Are we supposed to be looking at your paper, or you're just saying that out loud?
No, I'll show you the paper.
Oh, okay.
But yeah, let me show you my, yeah, no problem. Let me show you my paper.
I was just asking because if you wanted to show us, we weren't seeing it.
You weren't seeing it. Yeah, no problem. Thanks for pointing that out. And there you go. So that's the masterpiece I'm creating. Okay. Now, let's see. And then here's the junction and the resistance here. And this goes all the way to the next node. And then this one comes down. There is a battery source resistance, and that's that one. The arrow goes to the left here. And then the last segment, it comes here, goes to the right, resistance, and a voltage source, and it goes back up. The arrow is in this direction. Okay. Now, I'm going to label these 1, 2, 3, and 4. Again, you're welcome to go 1, 2, 3, 4. It doesn't matter. They're just labels. Now, here's 14 volt. This voltage is 25 volt battery. Down here, there's an 8 volt battery. This would be I6. This one is I5. This one I4. I'm just copying from the book, folks. That's how he labeled them. And this is 1, 2, 3, 4, 5, 6. The voltages I got, that's 8. And this is 25. That's 14. There are 3 sources there. The resistance, R1 is 3. This one, R2 is 2. R3 is this one. R3 is 4. R4 is 2 and almost done. R5 is 1, and finally R6 is 1. So there you go. That's our network. Now, I was pointing to the direction of these. Again, the arrow from 1 to 2 goes to the right, wraps up, and completes the circuit, right? It goes like this in a counterclockwise direction. So I'm just going to go like this. That's the flow of the current in the top portion of that network. In the middle, see how it goes to the right, comes through, goes left, comes back up. And I believe, yeah, there is an arrow here. Sorry, I left it out there. That's how we know. So it goes to the right, goes through, turns left, goes back up. So that flow is in a clockwise direction. And finally, this one is clearly in a counterclockwise rotation. So that's just the flow of current through this network. Now, according to Kirchhoff's law, the first law, we're going to apply the first law to the junctions. The first law had to do with the currents, right? I'm going to go to the book and just read that to you. It'll be easier. So the first Kirchhoff's law says that all the current flowing into a junction must flow out of it. Here's a junction. All the current flowing into it should equal to the flow out of it. Remember, now into junction 1, we got flow from the top and we got the flow from the bottom, right? And this would be out. So with that in mind, by all means, let's see how this would be done. This is exercise in section 1.3, number 32. So first law applied to junctions. Junction 1. What would Kirchhoff's first law, sum of the currents in equal to currents out? So what would it be at junction 1? The current flowing.
Would it be 3?
Okay.
Well, what's the number of the current? Is it R sub 1 equals 3? Is that the current or what's the current?
Yeah, thank you. R is the resistance.
Okay.
I is the current.
I is a current. Okay. And what's our I sub 1? What is it? Oh, we
This
don't
is
have it, right? It's unknown.
exactly. We're trying to solve
Okay.
this, right? So we're going to find this based on that drawing and these numbers.
So would
So
it
go
be
ahead.
I sub 1 equals I sub 3?
Let's.
And oh wait, I'm sorry, I see. I sub 1 equals I sub 2.
Is it I sub 1 coming in leaves I sub 2? How about this 1 coming in? Isn't I 3 coming into 1?
Oh yeah, so it's I sub 1 plus I sub 3 equals I sub 2.
You got it. I sub 1 plus I sub 3 equals I sub 2. Perfect.
I
That's
had a question.
yes.
Would we include the 14 volts?
Oh, for this part, no, we don't, because he's asking for to find the currents. The currents. Here's the equation: V equal IR, right? So if we want to know what I1 is, right? I1 is VR. So for this one, let's see, I1 is equal to V over R. The voltage is 14, resistance is 3. So it looks like flow through this one is going to be without any of these restrictions we're put in. This is how you would calculate the current using that formula. But what we're doing is for the entire network, we're just looking at the flows in equal flows out. And that's what we want to do for this one.
Thank you. That makes sense.
Okay, you're very welcome. All right, let's do this. Now, so junction 1 is that. How about that junction 2? Junction 2, how would the currents work at junction 2? You got current 2 coming through, right? And this one is leaving because he's counterclockwise, right? So you got I2 going in, and what is leaving?
I sub 1.
I1, right? The current, this is the current. I1 is leaving. And how about this one? Let's see, there is an arrow for this one. So sorry, I left it. That's the arrow for this. Remember, it's clockwise. The middle network is clockwise rotation. So it goes this way, down to the left and up. So at junction 2, you got I2 coming in, I1 leaving, I4 leaving. True? So how are we going to write the current equation for junction 2? This is going in. Coming out is this one and this one. So that would be coming in. So wouldn't I1 plus I4, shouldn't the sum of these equal to what feeds into that junction, which is I2? Got it. So we're going to write I1 plus I4 is equal to I2. And let's do junction 3. We're looking at this junction now. For this one, leaving, entering, right? Leaving, entering. So what would the equation look like?
I5 equals I3 plus I6.
Perfect. Excellent. I3 plus I6 equal I5. And let's see, we got junction 4. How about junction 4? That's the last junction. That would be, again, it's coming in flowing in, out, right? In, going in, coming out. So that's going to be I6 is feeding through, and I4 is feeding it. So would it be I4 plus I6 equal I5? Does that make sense?
Yes.
Okay. So now notice, by the way, we handled these three using first law. Let me just put here. We're using the first law. That's what we did. First law. Now, let's see. And then we have, let's apply. So far we got 1, 2, 3, 4 equations, right? And we need more equations, see if we can come up with more. Let's apply the second law. In the second law, I'm going to read the second law for you. The second of Kirchhoff's law reads, the sum of the products IR, and remember IR means voltage. The sum of the product IR, that's current times resistance, around the closed path is equal to the total voltage in the path. Okay, so now to help you with this one, let's say for this one, the voltage is 14, right? To calculate the voltage through each of these resistance, we have to do IR, right? V is IR. So for this first resistance R1, we do I1 R1. That would be 3I1, wouldn't it? So I'm going to write 3I1 plus. For this resistance is I2. R2 I2, because we're doing voltage IR. So you do multiply its I by its R. R2 I2 would be 2, because R2 is 2 ohms. 2 I2. That's going to be 2 I2 equal 14. Is everyone okay on that one? Again, we're doing voltage equal current times resistance. For this resistance, the voltage through here is going to be I1, R1, but then we have a number for R3. So I just plugged in the 3 here. Let's look at the middle part. The middle part, the voltage is 25, isn't it? Right here, that's 25. Now, let's see. We have one resistance here, one resistance here, one here, one here. Don't we have 4? 1, 2, 3, 4 resistance, right? Each of these will have its own voltage, 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 voltage. And each of these, the voltage is IR for that resistance. So what would the voltage be for this resistance, through that resistance? It's going to be I2 R2, isn't it? And R2 is 2. So it's going to be 2I2 plus. What would it be for this one?
2I4.
Thank you. It's I4, R4. R4 is 2, so it's 2I4 plus 2I4. And for this one, R5 is 1. This is 1. 1 ohms.
1I5?
1I5, you got it. So that's just I5. And finally, this one, what's the voltage through that resistance?
4I3.
4I3, perfect. Awesome, got that one. And finally, the last portion of this network. Here's the 8-volt source. That's our 8-volt source. And what's the voltage through this resistance R6?
It's 1
One.
I6.
You got it. So it's just I6, one I6. And what is it through R5? This one?
1 I5.
You got it. And there. So we've got all these equations, right? Now, we have 6 unknowns, correct? Do we not need 6 equations? We have 3 equations here. I'm keeping track of equations now. We have 4 equations here, don't we? And that's 7, huh? So we actually have more equations than we need. So that means one of these is redundant or extra, isn't it? So which ones are we going to use? We could use, let's use this one, first one, second, third, and then let's use these 3. Is that okay? We're going to use it. In other words, junction for this one, I'm going to say this one is extra. Because we have 6 unknowns, don't we? All I need are 6 equations. If I come up with 7, 8, 9, 10 equations, it's just, those are redundant. We don't need it. We need exactly 6, as many as variables. So is everyone okay with that part?
Yeah.
Okay. So now let's do this.
Because, I mean, just to reference what you said in the past is like you can't have more equations than the variables that you have. Something like that.
Exactly. It is redundant. We never need more equations than variables. So let's say I have 5 variables. If you give me 14 equations, 9 of those are going to be redundant. And later we talk in chapter 2 about linear combination of equations. So my made up example, I have 5 variables. You give me 14 equations. That means 14 minus 5. 9 of those are going to be linearly dependent on the other 5. So they don't provide anything above and beyond what we already know, those extra 9 equations. In the case of number 32, we have 1, 2, 3, 4, 5, 6, 7. One of these is redundant. And it doesn't matter which one, by the way, you can eliminate. Any one of these, it doesn't matter. Because these are independent equations, right? Within each self. So drop any one of them and keep 6. And you'll see the answer will not change. So I'm going to let this one go. Because equation with 4, 6, 5, we actually have those, right? We already have them scattered throughout here. I got here's the one with I4, here's with 6, with 5, 5, 4, 5, 6. So they all have representations. Let's write the matrix. Now, what is the first equation for this one? Remember, we want to write this in the form of matrix of coefficients. So how would I rewrite the first row of this matrix? What is it going to look like?
I sub 1 plus I sub 3. I mean, I sub 1 plus, oh, never mind. 1 plus 1. I mean, negative 1.
Very good.
Plus 3. I mean, plus 1.
Perfect. Thank you. Okay, I1, that coefficient is 1. There it is. I2, bring it to the left, becomes negative I2, doesn't it? And there is I2. And I3, this coefficient is 1. Now, the coefficient for I4, 5, and 6, they would be 1, 2, 0, right? Because this first equation does not have 4, 5, 6. So these are the coefficient on I4, 5, 6. And what do I have at the end here?
0.
0. And here's the reason, folks. I1 minus I2 plus I3 is 0, isn't it? Isn't that what this equation reads?
Indeed.
So you see that 0? That's That's this zero that you see here. There. In other words, there you go. The very last column is going to be the column of the constants, right? What's to the right of equal sign. Once you move all of these to the left, this one we're going to ignore. Move left, keep, right? So let's see what it's going to look like. Now, what about the second equation? What is that going to look like?
So 1 plus, -1,
Thank you.
and then plus 0,
Plus 0.
plus 1.
Excellent.
And
You
then
got I1, 2, and 4. So it's 1, 2, 4. So that means 3, 5, and 6 must be 0, right? Because they're not in the equation. And that would equal to 0. The third row would be coming from junction 3, this one. What is I1 in this equation?
I had a question, Professor.
Yes, Ariana.
When I wrote the second row, I had the first and fourth ones as negative and the second one as positive. Does that affect the outcome?
Oh, I see. It wouldn't, no. Let me write the second one. So here's I1, bring I2 over, keep the I4 equals 0, right? So with this, you're going to see 1, -1, 0, 1, 0, 0, 1, 2, 3, 4, 5, 6, and 0, right? Isn't that row? That's what we have.
Yeah.
Now, so what you did actually, you kept I2, you moved these others to the other side, right?
Yeah.
Okay, so yours actually looks like this, and which is fine. This would be now what? I1 is negative, so you have -1. I2 is 1, I3 is 0, I4 -1. Here's 5, 6, and the number, correct? So
Yeah.
that's what you have. Now, you're fine because look at the one we have, look at the one you do. Remember, property number 2 of the elimination method, you can multiply a row by a constant, non-zero. If you multiply ours, the way it looks by -1, what are you going to get?
The one that I got.
You got it. So no, you're going to be fine. And if we were to, we're not going to, but if we were to do this by hand, get it to the reduced row echelon, in the end, we all get the same result.
Okay, thank you.
You're welcome. Yeah, thank you for pointing that out. No problem. So as long as, and again, like first row, somebody says, oh, you know what? I got -1, 1, -1. You're fine. As long as every one of those is opposite in sign. Okay, we're good, everybody, on this one. Sorry, let me enlarge that. I don't know what happened. Okay. Now, let's do the third row. What is the third row going to look like? That's coming from junction, this one. The third row doesn't have I1, I2, I4. Agreed? This one?
yeah,
No I1, no I2, no I4. No I1, no I2, no I4. Now, I3, 1. What about I5?
-1.
Very good, -1. Because see, I5 is on the wrong side. You need to move it over, bring it to the left. It becomes negative I5. And I6 is there. That's going to be 1, and that's going to be 0. Good. Now, let's look at these 3, the ones from the second law. So what would be an equation? I'm sorry, not equation. We already have the equation. What would be a row equivalent to that equation?
3, 2, 0, 0, 0, 0, 14.
Thank you. Perfect. And the next one. There is no I1 in here.
maybe 0
Yeah, go ahead, Jesus.
plus 2 plus oh, there we go, plus 4
4
plus 2
plus 2
plus 1
plus 1,
plus 0,
0, and that all of these should equal to,
25.
got it. And let's finish it off with this one. The last equation doesn't have 1, 2, 3, 4, right? Those are each coefficient 0. It only has 5 and 6. So here's 5, 6, and there's 8. Everyone okay on this? And then we're going to go to Symbol Lab now. And you will see, I'll put these in. We get the Gauss-Jordan, and let's see what happens. Is it okay if I go to Symbol Lab now?
Yes.
Thank
Yeah.
you.
Yeah.
All right. Sure. Let me do that. So I'm going to stop this share and share Symbol Lab. Got it. Now, the size of the matrix we need. What size matrix should we grab?
6 times 7, 6 by 7.
Good. It's going to be a 6 if you count the rows and columns in the very last matrix we did together. We got 2, 4, 6 rows, 2, 4, 6, 7 columns. Thank you. So we're going to go down here, and again, because it shows on top what it is, so I can go a little crazy here. And let's see, 6 by 7. So there's 7, and there. I'm looking at the number on top here. There you go, 6 by 7, left click once. Boom. Isn't that awesome, folks? I love this thing. It's just, it really makes our lives so much easier. And you're welcome to use this. In fact, you should for your exam, for your homework, everything. 1, 2, 3, 4. And then we go 1, negative 1. I'm going quick because I'm sure everyone is okay with this part. The third row, 0, 0, 1, 0, negative 1, 1, 0. The third one is 3, 2, and then 4 zeros. 1, 2, 3, 4, and 14. And then we go 0, 2, 4, 2, 1, 0, 25, and last one, 4 zeros. 1, 2, 3, 4, 1, 1, and 8. So please check, just make sure I didn't goof anything up. Does that look? I'm just checking my paper against that. I think it looks.
I think you did it really good.
Thank you. So it looks okay. Now, let's hit go. And remember the way, wow, see how long it took it to do that? It would have taken us a long time. So remember, the first part is the echo of what we put in. So that's not the answer you see here. So scroll it. That's just the echo of what it says. This is what you gave me. And here's, beautiful. Check this out, guys. Isn't that cool? There is your Gauss-Jordan. So now what I'm doing, I'm copying that matrix on my paper. So I got, and I go by column. So I got 1 and then 2, 4, 5 zeros beneath it. So there you go. I just copied the first column. Second column, 0, 1, and then all zeros. And then third one, 0, 0, 1, and a bunch of zeros, everything 0 below that. The fourth column, I've got 3 zeros, a 1, and a couple of zeros. The fifth one, wow, isn't that gorgeous? This beautiful matrix. I'm gonna take a picture of this, hang it in my bedroom. 1, 2, 3, 4, 5, and a 6. 1, 2, 3, 4, 5. Wow, beauty. And then we go 2, 4, 2, 2, 5, 3. 2, 4, 2, 2, 5, 3. There you have it. And there we go. And we have everything worked out. So this system is now solved, isn't it? Is everyone okay on the solution first? And then we'll just copy the solutions now. If we are good on the solutions, thank you. So I'm going to stop this share and I'm going to share my handwritten work. And there you go. So I just, as you can see, I just copied that. Now, remember these are coefficients, first column, I1, I2, I3, and so forth. So what does this last row tell us? What's an expression for this?
I6 equals 3.
Thank you. I6 is 3. This one. I5 is 5. I4, beautiful. This one has a unique solution. I3 is 2. I2 is 4. And I1 is 2, right? Are we good on this one?
Yes.
Now, real quick, let me back up. Remember I said this equation is extra? Let's actually type this one in. So I'm going to change my share. Let's see, stop share, and then change my share to back to Symbolab. All right. And this time, let's see. I'm looking at the one I said is extra. That equation was I4 minus I5 plus I6 equals 0. Please look at your notes. The one I said extra is I4 plus I6 equal I5. Bring I5 to the left. So we go I4 negative I5 plus I6. A row for this, wouldn't that be 0, 0, 0? Because I don't have 1, 2, 3. I4 negative I5, I6, 0. Is everyone okay with the one I called out? The one that I called extra, it's going to be 0, 0, 1, negative 1, 1, 0. Now let's go here. And we're going to put in now, we have an extra equation, right? So now I'm going to have 1, 2, 3, 4, 5, 6, 7 equations and 2, 4, 6. So it's going to be a 7 by 7, right? And there you go. So it's a 7 by 7. I'm just going to real quick retype these. So here's 1, negative 1, 1, 1, 2, 3, 4 zeros. Second row was 1, negative 1, 0, 1, 1, 2, 3. And then we have 0, 0, 1, 0, negative 1, 1, 0. And while I'm doing this, by the way, Ariana, if you like, remember your second row was different from ours because you had multiplied by negative. Yours,
Yeah.
if you like to enter actually your row, not the one we did, and rerun it if you want to, you don't have to, and you will see you get the exact same outcome. 3, 2, I got 1, 2, 3, 4 zeros and 14. This was equation 4. And then I have a 0, 2, 4, 2, 1, 0, 25. Almost done, folks. 1, 2, 3, 4. And then we got what? 118. Perfect. And now the last one is the equation I said is extra. The one I didn't show you, I'll show you my paper in a moment to see what I had. But this is the new one, new row. The one that I said was extra. Oops. I know you got it. It's negative 1. All right. This is the equation that was extra. It was I4 plus I6 equal I5. Bring I5 to the left, you get negative 1. So check this out. Go. Aha. Isn't that cool, folks? This is just amazing. Look at the last row. What do you think? The solution didn't change, right? Remember? before I did this? Wasn't this the solution? 3, 5, 2, 2. So the solution hasn't changed. And look at this last row of zeros. You see how that worked? Anytime this happens, there's nothing wrong. It's like, oh my God, doesn't have a solution? No, it does have a solution. All this tells me is that one equation is redundant. And that's why I said, let's call that junction 4 extra, because I only had 6 unknowns. Why do I need 7 equations? And that's what you get when you have more equations than unknowns. So hopefully this puts it in perspective for everyone. Is everyone okay with this, with what we just did?
Yes.
Yeah.
Fantastic. So let me, real quick, and we are done with this section, by the way, folks. And in fact, wow, 9 o'clock, time flies. My goodness. I guess time flies when you have fun, right? And I do have fun. Okay, let me stop this one. I'm going to change here. I'll let you guys go in just a moment. I know it's getting late, but I just want to show you what I mentioned. There you go. This was the extra equation. That was this one. Remember the one I said ignore it? So I went ahead and rewrote it. 1, 2, 3. I1, 2, 3 are 0, 1, 2, 3. That's 1, negative 1, 1, 1, negative 1, 1, 0. And there you go. What do you think, ladies and gentlemen? I hope you had as much fun as I did. Is everyone okay on what we've done here this evening? Now, let me do this. I'm going to actually get out of this. And now I can actually put the video back on. And again, I don't see my own self in here. I'm hoping you can see me because I have my camera on and my OKO.
We can see you.
Oh, okay, fantastic. Yeah, this is the one I'm using, folks, to write on. It's called OQ Cam, that one. That's what I'm saying. I keep reconnected because the device cannot have 2 videos at the same time. So when I use this, I have to turn my video off. But anyway, is everyone okay what we did this evening?
I think it has to digest. Like, I mean, you know, like, let it, you know, ponder in the mind, and I think we'll get it. It doesn't look too complicated.
Fantastic, fantastic. And again, that symbol app, folks, I told you, it's really godsend. It's amazing. It's going to help us so much because later on, Gauss-Jordan is just portion of what we will be doing. So for that reason, we don't really want to spend 20, 30 minutes just to get the matrix in the 1010 format. So we're definitely going to use that over and over. So we are done for this evening. Let me stop this recording. And then